Hello and thank you for joining us. My name is David Hall, Product Manager with National Instruments, and today I'm going to explain how to measure sensitivity with a GPS receiver. Now, what I have in front of me is actually an eval board for a GPS receiver, and it's using the SURF3 chipset. Now, what I'm going to do is I'm going to talk to that through this serial port, and then I'm going to apply a direct connection to this SMA connector. Now, this receiver, typically, when it looks at the sky to track GPS satellites, it will see a power level of maybe negative 130 dBm from each of the satellites that it's looking at. So what we're going to do is we're actually going to simulate the same signal that this receiver would observe in the L1 GPS band by simulating 9 independent satellites. Now, we can actually simulate up to 12, but we're only going to use 9 based on the location selected. So what I'm going to do is I'm going to connect this receiver to a vector signal generator through this SMA cable. And with my PXI system on the right, I'm actually going to simulate a GPS signal. So essentially, this satellite will think that it's seeing satellites in the sky based on the signals that we're generating with our vector signal generator. Now, to explain sensitivity, what we're going to do is actually look at a little bit of theory on the board. Now, what I've shown here is that the RF power that we apply to our device under test will actually affect the carrier-to-noise ratio that we read back from the receiver. So we can see that power equals negative 174 dBm per hertz. That's the thermal noise floor, plus carrier-to-noise ratio, plus noise figure. Now, this receiver has a noise figure of about 4 dB with the front end I have on it. So we can actually graph the relationship between RF power and carrier-to-noise ratio according to this equation. And what we observe is that as the RF power decreases, the carrier-to-noise ratio for each individual satellite will also decrease. Now, based on the chipset, we actually define a minimum C to N value of 28 dB-Hz. Now, that's the minimum value required by our receiver to obtain a position fix for the first time. And so, based on this equation, we can see that the sensitivity should be negative 142 dBm based on this C to N value. So, going over to our demo, we can see that the power level that we're currently generating at is negative 130 dBm. Now, that's the power level, that's the minimum power level that a satellite would expect to see in an open sky. And then we can pan over here and see that the carrier-to-noise ratio at this particular power level is between 39 and 41 dBm-Hz. Now, you notice these colors just turn from blue to green. And that occurs because my receiver actually just obtained a position fix where it can report its latitude, longitude, and altitude. So the fact that this is green tells me I've achieved a position fix. And based on this relationship, we can observe the relationship between the power and the carrier-to-noise ratio. So what I'm going to do is actually lower the power level supplied to the duct and see how the carrier-to-noise ratio responds per our equation. So we're currently at negative 130 dBm. We're going to go down by 5 dBm, and we should see these carrier-to-noise ratios settle on the order of 35 to 36 dB-Hz, which we see right here. In fact, I can go down by another 10 dB. So at negative 145, I should see a carrier-to-noise ratio of 25 dB-Hz. So what this illustrates is that there's a linear relationship between the carrier-to-noise ratio reported by the receiver and the power supplied to it. In fact, this actually motivates a couple different measurements that we can do based on the carrier-to-noise ratio. The first one that we saw is sensitivity, which we can simply track the lowest power level at which our receiver will lock. And so, according to our estimates, we should see a sensitivity of negative 142 dBm. And if we look at the C to N, our C to Ns are just about 28 dB-Hz at the value we would expect. So based on this demo, we can see that sensitivity measurements can be made on a GPS receiver simply by adjusting the RF power to the appropriate level. So I hope this session was helpful for you and that you understand a little bit more about GPS receiver testing. For more information, visit ni.com/RF.